All right, students, today we are looking at lesson 3 of Unit 10, the solar system. The sun, it gives us life and it is the biggest killer in the solar system. All of our energy comes from it, but also we need our atmosphere to protect ourselves from it. Because if we didn't protect ourselves from the sun, we would die. So it is the great life giver and the great killer of the solar system. So let me hit this up with a present. The sun. What are the properties of the sun? So we're going to be talking about here are our wonderful SOLs. What do we know about the sun? The sun is the closest star to Earth. The sun is a star. When we look up into the sky and we see stars, those are other suns out there with different solar systems in outer space. The sun rotates once about every 27 days. The sun's diameter is about 87,000 miles. A million Earths could fit inside the sun. The sun is 74% hydrogen, 24% helium. So that adds up to 98% of the sun is hydrogen and helium, and it's almost all the mass in the solar system. So the majority of the mass in the solar system is hydrogen and helium atoms, which are very simple atoms. The core of the sun is around 27 billion degrees Fahrenheit. That's hot. What is the structure of the sun? Well, it's got a core. In the core, nuclear reactions happen here. That is where the energy is produced. We'll talk about that later. The radiative zone. Energy is transferred away from the core of the sun. Remember how we've talked about energy transfers? Um, so the energy is moving from one place to the other through different ways. Convective zone, convection currents, the ones that spin, move energy, the outer layer of sun. The photosphere is the visible surface of the sun. That's what we see. The chromosphere is the middle layer of the sun's atmosphere. The sun does have an atmosphere. And the corona is the outer atmosphere of the sun. And here we see a picture, a diagram of the sun. Boom, nuclear reactions. This is where all the energy in the universe is being, in the solar system is being produced. We have the corona, which is on the outside, the convection zone, moving heat, the radiative zone, coronal streamers, chromosphere, sun's core, very complex thing that is creating all the energy. How do we have nuclear reactions in here? The gravity is so intense that it is actually fusing atoms together. When they fuse together, they make a tremendous explosion. What we've only been able to do here on Earth is split atoms. In the sun, the atoms are actually combined because of the great pressure. The sun has 6 main zones: corona, chromosphere, photosphere, convective zone, radiative zone, and the core. So let's take a look. The sun.
While billions of stars are scattered throughout the universe, the one at the center of our solar system plays a special role for us here on Earth. Our sun formed about 4.5 billion years ago in the Milky Way galaxy's Orion Spur. It was born when a cloud of dust and gas, known as a solar nebula, collapsed. And in the middle of this formation, matter condensed into a burning ball of gas that became our sun. The sun's fiery nature, along with a tremendous gravitational pull and an extensive magnetic field, helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere, the photosphere, the convective and radiative zones, and the core. In terms of atom count, the sun is about 91% hydrogen, the sun's fuel, 8.9% helium, and 0.1% heavier elements, such as carbon and nitrogen. Due to the sun's extreme temperatures, these elements stay in a gas-like phase called plasma. In the core, temperatures reaching at least 27 million degrees Fahrenheit combined with the sun's powerful gravity, fuse together hydrogen molecules to create helium. Called thermonuclear fusion, this releases an enormous amount of energy in the form of radiation, electricity, solar wind, and, as we experience on Earth, life-giving heat and light. Such volatility is contained thanks to the sun's tremendous gravity. It's strong enough to hold the solar system intact and is primarily due to the sun's size and mass. Our sun is the largest and most massive object in the solar system. It's more than 100 Earths wide and could theoretically fit all 8 planets inside nearly 600 times. It also contains approximately 99.8% of all the mass in the solar system. Because of this mass, the sun has a great pull on the fabric of space, creating a gravitational force that causes nearby planetary bodies to be drawn toward it. This gravitational pull allows the sun to hold together a system of 8 planets, potentially dozens of dwarf planets, at least 170 moons, and countless comets and asteroids. Without the sun's gravity, these celestial bodies would drift off into deep space. Another critical property of the sun is its magnetic field, which encapsulates the entire solar system. Called the heliosphere, this force field protects the planets from harmful cosmic radiation. It's caused by the sun's plasma pushing electrically charged particles toward the star's poles. This process turns the sun into a giant magnet. Although the sun's magnetic field is invisible to the naked eye, its effects are noticeable. On the sun's surface are dark areas called sunspots, which mark strong pockets of magnetism. On Earth and on some of the other planets, the sun's magnetic field interacts with their atmospheres, resulting in beautiful auroras. Despite its size and strength, the sun will not last forever. In about 6.5 billion years, it will run out of its hydrogen fuel, expand to envelop Mercury, Venus, and even Earth, and then collapse into a small star known as a white dwarf. In the meantime, the sun will continue to play a critical role in the system that bears its name. The sun's protective magnetic field, tremendous gravitational pull, and ability to create vast amounts of energy will protect, contain, and give life to our solar system.
The sun. Nuclear fusion, process by which 2 or more low-mass atomic nuclei fuse to form another, nuclear reactions. How does the sun produce energy? The crushing force of the gravity in the center of the sun combined hydrogen atoms into helium atoms. Remember, matter can never be created, can never be destroyed. This gives off a nuclear explosion. Nuclear fusion powers the sun. So what happens? Here's hydrogen, hydrogen, and because of the great density and pressure, they slam into each other to form a helium. Then this little electron goes flying off, and there's energy. So here we see things slamming together. They do not get broken apart, they get forced together.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take 2 hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get 2 atoms to fuse. 2 protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. they have to come together with a huge amount of energy or velocity to get close enough to begin to fuse. And that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
And that's the sun and how big it is. It's an amazing thing how that's produced. So the energy is transferred from the sun's core, where we saw with all those nuclear reactions going on, through the radiative zone and convective zones to the sun's surface. Hot rising gases and colder sinking gases form convective cells in the convection zone. It's almost like the ocean. Remember how we said when things cool off and heat down, that creates motion inside? Same thing with the sun. It's incredibly hot in the center and it's radiating to the top. Once it cools down from the top, it starts to sink, and here we have these wonderful little convection zones, which look like our air currents or our water currents. Kind of the same thing. Thermal transport in the sun.
Energy is produced in the core of the sun through nuclear reactions. Small nuclei combine to form larger nuclei in nuclear fusion and release energy in the process. That energy then makes its way toward the surface of the sun. There are three major modes of thermal transport: conduction, convection, and radiation. This is the first of two videos looking at thermal transport in the sun, and will specifically study radiation, which is the dominant mechanism in the inner part of the sun. High-energy photons are produced by the proton-proton chain in the core of the sun. Note that the density of the plasma here is very high so that the photon can travel only a very small distance before it collides with an electron and is redirected. Thus, the photon is bounced around repeatedly, very slowly making its way out of the sun in what is termed a random walk. We can conceptualize this photon random walk using the Bumble Ball, a vibrating and bouncing toy for children and dogs made by Ertl Toys that costs about $12. We will place a number of Bumble Balls at the center of a pattern of concentric circles meant to represent photons at the center of the sun. You can think of the photons as escaping from the sun when they pass the outermost circle. You can see already that it is going to take quite a while. Calculations indicate that the energy from a typical photon takes over 100,000 years to escape from the sun. That's the best way to say it, to talk about the energy of the initial photon getting out, since it really isn't the same photon anymore. Note that convection becomes the more important transport mechanism once the temperature has fallen to 100,000 Kelvin and atoms are not completely ionized. This occurs about 70% of the way out. More teaching materials can be found on the web at astro.unl.edu.
So there is that wonderful process. Here we go. Convection.
Small nuclei combine to form larger nuclei in nuclear fusion and release energy in the process. That energy then makes its way toward the surface of the sun. There are three major modes of thermal transport: conduction, convection, and radiation. This is our second video looking at thermal transport in the sun, and will specifically study convection, which is the dominant mechanism in the outer part of the sun. Convection is the actual movement of material in fluids due to buoyancy. Hotter material has relatively lower density, and thus it rises, much like a hot air balloon. Cooler material has higher density and thus it sinks. We can easily illustrate convection with the following equipment: hot plate, small pan, silicone oil, and aluminum powder. We simply place our silicone oil and aluminum powder mixture into the frying pan and heat. It is possible to ignite the oil, so one wants to know the safe temperature range for the specific type of oil they are using. Very high temperatures are not needed in this demonstration, and I have set the thermostat for 350 degrees. As the oil heats up, convective cells are created. Hot material, initially in contact with the bottom of the pan, moves upward and boils over. Cooler material then circulates downward. The aluminum powder serves as a tool that allows us to see the circulation.
So there you see it rises as it
Convection
cools
like
off or
this on the
falls
surface of
down.
the sun is known as granulation. The material that is moving upward at several kilometers per second toward the surface appears brighter, and the cooler material moving downward is darker, giving the sun this mottled appearance. Convection cells on the sun are about 1,000 kilometers in diameter. More teaching materials can be found on the web at astro.un.
So, interesting. Sunspots are dark areas that form on the surface of the sun. A solar flare is an explosive release of energy on the sun. Radiation is released, and a prominence are huge loops of cooler gas that reaches down back to the sun. Looks like a bridge. So, these are actually things on the surface of the sun that can affect our life here on Earth. Sunspots, solar flares, and prominence are three kinds of solar activity that occur on the sun's surface. They can affect our life on Earth and can damage electronics and internet. So there is a wonderful prominence. It's almost just like an eruption or an explosion, but when this happens, it is throwing out a lot of energy in one direction. So, sunspots.
At Kitt Peak Observatory in Arizona, solar astronomer Matt Penn studies this solar surface to discover how photons of light get trapped.
There's a bunch of theories today, but hopefully we'll get some data.
Using the McNath Pierce telescope, he focuses the sun's light to scan the photosphere in detail.
So what we've got are a few small sunspots on the disk of the sun. We've got two sunspots, two large ones. They're heading off to the edge of the sun, to the limb of the sun. But they're all accompanied by smaller sunspots, groups of smaller ones following them.
Sunspots mark areas where light is trapped.
So a sunspot forms a dark spot by removing energy from that part of the sun. It's blocking the convective flows that transport the heat and the light from inside the sun to space. And so what we see then is a cooler region that appears dark to us.
A powerful force stops our photon dead in its tracks, preventing its light and energy from leaving the sun's surface. That force is magnetism. Sunspots take shape where intense magnetism from deep inside the sun blasts up through the photosphere.
The magnetic fields are so strong that it actually stops the convective motion of hot inner material from flowing to the surface. So you actually get what looks like a cool spot on the surface of the sun.
They can be huge, the largest over 10 times the size of Earth.
Sunspots. Here's a prominence different than a sunspot. So there is this prominence letting off the energy. And pretty cool video about that. And another eruption if you would like to watch it on your own. So we have sunspots, solar flares, prominences. The tough thing about this is these will give off extra energy than we're used to on Earth, and they will mess with cell phone receptions. There was a bad one 6 or 7 years ago that missed the Earth, that kind of gave us a glancing blow. And if it would have been a direct shot to us, it probably would have shut down the internet on us. And I cannot imagine internet and Wi-Fi being fried. So this is one of the things that, just one of the things that could possibly happen. Not that it's going to happen or ever has happened, but it's one of the things that when people study the sun, this is why it's important to keep an eye on things like this. Summing up, the sun is composed of layers, and energy is transferred from the sun's core to the photosphere. So you see how all this energy is created at the sun, and it moves out, and then it is transmitted to us on Earth. We have to be very careful with the sun. The sun gives us life, the sun gives us energy, but the sun can also take us out. And is also one of the things that we are constantly studying. What we will learn more and more about the sun as the years goes on and as our technology advances. But right now, this is what we understand of our sun. So, thank you, students.